yeah, okay. I just started the recording, but I think we've only done some basic definitions, so it's all fine. Okay, so what are some examples of G varieties? So we'll start with some pretty basic examples. We'll get to more sophisticated examples later on. So some of the actions that we always have, that we automatically have whenever we have an algebraic group, are the action by conjugation. So here, if we take little g acting on little x, then we just conjugate little x by little g. So that's the conjugation action. We also have the action by left translations. So this is just multiplication, but we think of it as an action. And we also have the action by right translations. So this is multiplication on the right, but in order to make the group axioms work out, we need to multiply by the inverse. Yeah, so you can check. So it comes down to the fact that if you take the product of two elements, h and g, then their inverse is the inverses in the opposite order. So g inverse, h inverse. So these are actions that we always have. And yeah, so these two are instances of principal homogeneous spaces, or torsors. So that's so we said what a homogeneous space is. In a principal homogeneous space is where the action is transitive, and in addition, all stabilizers are trivial. So it's kind of, as an algebraic variety, the principal homogeneous space is isomorphic to the group, but we kind of think of it just as an algebraic variety, not as a group. So it's synonymous with torsor. So a torsor and a principal homogeneous space are the same thing. Maybe in some context there's some distinguishing features, but for our purposes, they're the same thing. Okay, so these are the easiest examples we have of group actions. There's of course the trivial action, so we can take any affine variety and let every element just act by the identity. That's the trivial action, and I guess we also have that. All right, so okay, so we'll also be considering representations of an algebraic group. We're going to call, so the definition of a representation. So representations are kind of like G actions, except on vector spaces where all the transformations are linear transformations. So representation is a homomorphism of algebraic groups from our group G to the general linear group of a vector space. So I guess in Springer they want to reserve this notion to finite dimensional vector spaces, but so I'll try to be consistent with that. But there's no barrier to considering these infinite dimensional representations, but I guess I want to be consistent with Springer and reserve the term rational representation for this finite dimensional case. So we see that, as I said, that the V becomes a G variety. So there is an action of G on V, and all these action maps are linear transformations. And of course, we can pick a basis for V, and then we get a map of algebraic groups from G to GLN. So I guess part of the reason we restrict V to be finite dimensional is because we don't want to be thinking about infinite dimensional varieties. We can define, there's a well-defined notion, but we don't want to go into that in this class because there are many subtleties. So we want to restrict our attention to the finite dimensional case. Okay, so great. So there's some exercises here. I'll let you know by email and post on the website which ones of these I recommend looking at and which of them are eligible for submission. Okay, so any questions so far? All right, so, okay. So I want to point out that I think I alluded to this fact earlier. I wanted to point out that any finite group is a linear algebraic group. So in that sense, the theory of linear algebraic groups encompasses the theory of finite groups. So how does this work? Well, let's start with a finite group and look at its group algebra. So remember that this is a vector space, finite dimensional vector space, and it has as a basis indexed by the elements of G. So E sub G is a basis vector, and we have one basis vector for each element of G. And this is an algebra where the algebra structure, so E sub little g times E sub little h is the basis vector E sub G times h. So yeah, I guess you're probably familiar with the group algebra. And we have the regular representation of G, which is its action on the group algebra. And this is given by the following homomorphism. So little g goes to the linear map that takes E sub h, this basis vector, to the basis vector E sub G times h. So this is just kind of shifting around the basis vectors. And this is a representation, and it's injective. So yeah, you can think about why it's injective, and its image is closed inside of the group. That's one of the results we mentioned. And so therefore it's an enclosed embedding of the group inside the general linear group. And we can, and by the things we've talked about, it's a closed subgroup, so it's a linear algebraic group. It's an affine variety. So now you may be asking, it's an affine variety, what's the algebra of functions? Well, it turns out to be just the dual of the group algebra. So it's the Hopf dual. Yeah, I don't want to go into it too much, but if you have a finite dimensional Hopf algebra and you take its dual, that's also a finite dimensional Hopf algebra. And if you start with this group algebra and you take its dual, then you recover the algebra functions on G with its Hopf algebra structure.
I have a question about the image. Why the image is closed?
So this is one of the results that I mentioned up previously.
Oh, you didn't say it's closed. If I'm correct, if I remember correctly.
Let me
Okay.
check.
Okay. No, well, maybe I missed. Okay.
Yeah. Yeah, it's closed. Yeah. So yeah.
It's unlike a regular morphism between varieties that the image not necessarily need to be closed.
Yeah, because we're doing
Okay.
algebraic groups. Yeah.
Okay. Thank you.
Okay. So yeah. Okay. So we have that finite groups embed inside of GLN. And now the next thing we want to prove is the embedding theorem. So so every linear algebraic group embeds as a closed subgroup of GLN for some n. So yeah, so this explains the name linear algebraic group. So every algebraic group that's affine turns out to be just a closed subgroup of GLN, and that's why we call it a linear algebraic group. Okay, so let's think about this theorem is true. So the idea is to think about the an action of G on its affine algebra. So this is the affine algebra is in general infinite dimensional and infinite dimensional K algebra. But we can still think about an action of G on this infinite dimensional K algebra. So if we take any little g, then there's a algebra homomorphism. In fact, it's an automorphism that I'll call rho sub g that takes f, a function on g, to the new function, which just first multiplies x on the right by g, and then you apply f. So yeah, so you can check that this is a K algebra homomorphism, and that so this may be confusing why we're multiplying by g on the right as opposed to multiplying by g inverse on the right, but this is the right thing to do, and you can check if you write out what the composition of rho sub g and rho sub h is, you'll see that this is the right. This gives the right formula. In other words, that composition is just rho of hg. I guess that's how I wrote it in the same order. The order is preserved. Okay, so we're gonna we're gonna be referring back to this K algebra homomorphism. So if I were in class in person, I would put this on the board and then have it be on the side and keep it there for a while. So I guess I'll just ask you to remember this and go back to this when necessary. Okay, so first we need this somewhat technical lemma, which says the following. So if we have a subspace of the affine algebra of G, then it's stable under this action. So rho sub g of v is contained in v if and only if we have this identity. So remember, we have a coproduct on the affine algebra of functions on G, and that coproduct maps from K brackets G to K brackets G tensor K brackets G. And the condition states that if we take V as a subset of K brackets G, as a subspace of K brackets G, that maps into V tensor K brackets G. So it's that's the condition. So and then the second thing we'll prove is that if V is finite dimensional, then there exists another finite dimensional subspace W in the affine algebra that contains V. So it's bigger than V, but it's still finite dimensional, and it has this equivariance property, the stability property. So rho G of W is contained in W. So if we just start with any random finite dimensional vector space inside KG, then we can find a bigger, still finite dimensional vector space that has this property, rho of G that's stable under rho of G, and therefore by part one, it also has this nice interaction with the coproduct. Okay.
Can you explain what does it mean, the inclusion to the tensor product? What does it mean that it includes inside?
Right. So in general, so in general, so do you remember that the coproduct goes from K brackets G to K brackets G tensor K brackets G, right?
Yes.
Yeah. So in general, if we have delta V, it'll land in K brackets G tensor K brackets G. That's from the coproduct where it starts and where it finishes. And the claim is that it lands in a subspace of K bracket G tensor K bracket G, namely that subspace where in the first coordinate we always have something in V. So yeah, I mean, I like to think about diagrams. Maybe a diagram would have been useful here. So K brackets G maps to K brackets G tensor K brackets G. V maps inside of here, V tensor K bracket G maps inside of here, and the claim is that there's a factorization of this map, so V, there's a dotted line in the bottom, V goes to V tensor K bracket G.
Thank you.
Okay. So, all right, so then how do we prove this? Well, okay, so we're gonna do so we're gonna start with this assumption and we're gonna prove this claim. So if we know that the coproduct sends V into this subspace, then, okay, what does that mean? That means if we take any F in V, so V is a subset of K bracket G, so it's, in particular, everything is a function on G. So if we take some function on G that happens to live in this subspace, then when we write it out, when we write out the tensor, when we write out the coproduct, it's a tensor, it lives inside a tensor product, so we can decompose it into simple tensors like this. And the hypothesis is that each of these F sub i's lives inside of V, and these phi sub i's are just some other elements of K brackets G. There's no hypothesis on them, they're just some elements. Okay, so what do we do with this? Well, let's see now. So if we take any, this is a little g, not a little y. So any x and little g in G, let's apply rho sub g to F and then evaluate at x. So remember, we're trying to show that rho sub g of V maps into V. So it's contained in V. So rho sub g of this F, which we assumed is in V, let's apply it to an element in G. So this X, and let's see what we get. Well, by the definition of rho sub G, we get this. So that's the definition we gave above. And now this XG is just the multiplication of X and G. So we have this mu here. And now remember that mu is the, so actually this statement, so this by definition is just the pullback of F under mu applied to X comma G. So this is just different notation for the same thing. And now we had a name for this pullback of the multiplication. That's just the coproduct, right? So that's where the coproduct came from by pulling back this multiplication. So we do the coproduct on F and we apply that to X comma G. So we have this formula for the coproduct on F. So we can just use the formula and plug the things in. And so we have this sum. So this lives inside of the ground field K. So we have evaluated this tensor product, and we've gotten something in the field. Okay, so hopefully that's clear so far. So now we want to know what rho G does to F. We evaluate it at this X, and this X appeared here. So that means that if we remove the X here, if we just think of this as an abstract function, that's the function that applies Fi to little x, multiplies it by this scalar, oh, sorry, this is a typo, this should be a G, and takes the linear combination. So let me fix that real quick. What's going on? So this should be, oops. Let's move this. This should be little g here. Let me put brackets around it. Okay, there we go. So, yeah, so hopefully that's clear. If it's not clear, then I recommend just sitting down and going through it at your own pace. But I think we'll move on. So let's do the other other direction. So if we already know that rho sub g of v is contained in v, then, okay, what do? We need to show this property of the coproduct. So first we need a bit of setup. So first let's take a basis of v. So f sub I, where I is some indexing set. So v is not assumed to be finite dimensional, so this could be infinite dimensional. This is just some indexing set. And we extend this to a basis of all of k brackets g by taking this, yeah, maybe this is bad notation to call them g sub gi, but we extend this basis to a basis for all of k brackets g. So this is some infinite dimensional basis. It's pretty big. And now we know that the coproduct has to be of this form. So we have to have some basis vectors here. We have to have the basis vectors here multiplied by some functions in k brackets g, and then we have these basis vectors here. And this, just to point out, just for sanity, only finitely many of the phis and psis will be non-zero. So this is a finite sum in the end. So yeah, hopefully you're familiar with like tensor products and how they work, and simple tensors, and how bases work, how the bases for a vector space reflects on basis for the tensor product. So we have this, and now we need to show, basically we need to show that all these things are zero, because that would show that this tensor product lives inside of V tensor k brackets g. So how do we do that? Well, we have to use our assumption, right? Our hypothesis was that rho sub g of v is contained in V. So let's apply rho sub g to this f that we fixed, and what do we get? By the similar sort of argument that I gave in the first part. So I haven't spelled this out completely, but we get this result. So this comes from taking this notation that we fixed, and using an argument similar to what was up here. So let me scroll up real quickly. So basically this computation here, and we just do it again basically with this notation, and we get this result. So the hypothesis that rho sub g of v is contained in V means that all of these must be zero. So we only stay in V. So Fi was the basis for V. We don't get anything outside of V. So all these must be zero. So psi sub j of G must be zero. And since this identity, I didn't say it here, but this is for all G. So since psi sub j of G is zero for all G, we know that psi sub j is zero. And that's what we wanted to show, because that shows that this the coproduct applied to F is contained in this appropriate subspace. So I think that concludes part one. Yeah, so that as I said, it's a bit technical. Maybe if everything I said didn't make sense, then maybe I'm happy to explain parts of it one more time, but it may be more useful just to sit down and work it out on your own. But any questions on this first part? Okay, so let's move on to the second part. So in the second part, I'll scroll back to remind you what the second part says. Second part says that if we have any finite dimensional subspace of the affine algebra of G, then we can find a bigger subspace that's still finite dimensional, that's stable under rho sub G. Okay, so how do we prove this? Well, we can prove it just in the case where the dimension of V is 1. So the reason for this is if we have V a bigger dimension, so still finite dimensional, then we can choose the basis for V, and we can prove this for each one-dimensional subspace of V spanned by a basis vector. And so for each of those, we get something bigger finite dimensional that's stable under rho of G, and then we can just put them all together. It will be a big space, but it will still be finite dimensional and still stable under rho of G. So that's why we can assume that the dimension is just 1. Okay, so we take, so since it's one-dimensional, it's just spanned by something. Some, I guess, F should be non-zero. Non-zero element in a non-zero function on G. And just like we were doing before, we can write it as, we can write the coproduct as the sum of simple tensors. So now we no longer have any assumption on this, on these FIs. They're just, the FIs and the phi are just some elements, some functions on G. And this sum is finite. So yeah, so then let's take W prime to be the subspace spanned by these FIs. And it's finite dimensional because this is a finite sum. And now what happens when we apply rho sub G of F? Well, the same computation that we did early on shows that this is just this, that's what it's given by. And this, and in particular, this lives inside of W prime. So for any little g and g, we get something that when we apply this map rho sub G, we get something that lives in this subspace W prime. And now there's, and now we think about W, which is a subspace of W prime. That's just the span of all these elements. So we're taking what looks to be an infinite set here, because G is, there's infinitely many group elements in G in general, and we're taking this set and we're taking the span inside W prime. But because W prime is finite dimensional, when we take this span, there will be lots of linear dependencies, and we get something that's just finite dimensional because everything is happening inside of W prime. So yeah, so that's what I just said. Dimension of W is less than W prime, which is finite. And so what about V? We want V to be contained in W. Well, that's just because if we do rho sub E of F, then we would just get F back. So that's actually coming from the co-unit axiom. So I didn't spell it out here, but the co-unit axiom tells us that F is just rho sub E of F. And then, oh, actually, we don't even need that, but it's much simpler than that. Yeah, let me not say anything more. So and now what about this claim that W is stable under rho sub G? Well, it's just that it comes from the fact that this is how we defined W. It's just the span of all these things. And we know that rho sub G composed with rho sub H is just the product. And so that's why this is stable under any rho sub G. Okay. Any questions on that proof? All right, so it's all, I mean, I think if you guys go back and if you're confused, it's all about understanding how this sort of, understanding why this is true. You just use this over and over again. And once you internalize this sort of procedure, then the rest of the proof is just linear algebra. Okay, so, all right, so now we can finally prove the embedding theorem. So the result that any linear algebraic group is a closed subgroup of GLN. Okay, so let's start with this observation that this the affine algebra of G is finitely generated as an algebra. So yeah, that's something we talked about. So let's pick some set of generators. So F1 through Fm, finitely many generators. Now let's take the span of these things inside the the affine algebra of G. So we're taking the span as a vector space. So these generate K brackets G as an algebra, but now we're just taking the vector space span. So we forget about the algebra structure. We just take this finite dimensional subspace inside of this infinite dimensional vector space. Okay, so this is some finite dimensional subspace, and we can apply the second part of the lemma above to find the W that's finite dimensional inside of K brackets G that contains V and that's stable under all of these rows of G. So that's what we proved in the lemma. And also by part one of the lemma, this is equivalent to the condition that the coproduct applied to W lands inside of W tensor K brackets G. And what do we do next? Well, now so we have this W, we had this, so V was the span of these generators up to M. And now let's pick a basis of W. So we can extend the basis of V to a basis of W. So now we have some more vectors, some more functions on G but we still have this generating set as a subset. So this whole set still generates algebra as a K algebra. Okay, so what do we do with this basis, and what do we do with this W? Well, all right, so since we know that the coproduct sends W to W tensor K brackets G, we know that we have to have for every, okay, so I claim that we have this sort of identity. Well, why is that? Well, we take one of these basis vectors, f sub I, we apply the coproduct. We know that the first factor in the coproduct will be in W, so it'll be these f sub j's will appear. So we just decompose it according to that basis, so f sub j's. And now we have something here that's some function in on G, some K brackets G. We don't know anything about it. It'll be zero sometimes it'll be non-zero. And we just call it phi sub ig. So it's like a coefficient. So this should be clear. And that same computation I keep referring to tells us that when we apply rho sub G to Fi, we get this sort of identity. So now here it's really a linear combination of the f sub j's with coefficients given by taking each of these functions and evaluating them at this G. So the G here is reflected here. Okay. Everybody good so far?
I have a question about before. Why is K bracket G is finite dimensional? Where did you assume it?
It's not finite dimensional, but it's finitely generated as a K algebra.
Why? Because it is a fine, G is a fine group, is a linear group.
And you can think of it that way, but for any algebraic variety, for any affine algebraic variety, the algebra of functions is finitely generated.
Okay, thank you.
Just by the way we defined affine algebraic varieties as algebraic sets inside a finite dimensional.
Okay, so this was not a basis, what you wrote up. It only was a generator. Okay.
Yeah, it's not a basis, it's just a generator. And it's not even a minimal generating set. So there's lots of flexibility in this proof. Okay, so now we have these phi sub ij's. So actually these phi sub ij's, so it's already a clue that they're indexed by two things, by I and j, and those two things run from 1 up to n. So it's already a clue that we'll get, they're a clue to how we'll define this embedding homomorphism. So now we're ready to define this embedding. So it'll be into GOW. So remember, W is the subspace of K brackets G that is invariant under these row of G's, that's finite dimensional, and that contains generating set for K as an algebra. So we define this map by taking G to a matrix whose ij entry is phi ij evaluated at G. And yeah, that's an n by n matrix. So yeah, so actually the rest of the proof is just checking that this is the right thing to do. So that this gives the result. So I won't go into it, but you can check that it's well defined. So for this, the only thing to do is to check that this matrix is invertible, but that's pretty straightforward. It's also group homomorphism, and that comes down to this fact here. And it's surjective, and the reason it's surjective is because, yeah, it's a little bit, maybe I wrote something about it. Yeah, so the reason it's surjective is because you can write down what it's induced from. It's induced from this map of algebras, this algebra homomorphism, and the generators are hit. So we hit the generators, and so that means that this is what am I saying here? Yeah, so Fi is in the image, so that means this is oh yeah, sorry, I totally mixed it up. So this map is surjective because the Fi's are in the image, and we pointed out earlier that if we have a surjective algebra homomorphism, then the corresponding map of varieties is injective. So let me correct that. Yeah. Okay, and I think, yeah, so that concludes the proof because we show that phi is a closed embedding. All right. Everybody good?
Do you know if there is a bound on n in terms of the dimension of G?
In terms of the dimension on G, yeah, I think so. Not right off the top of my head, but I think it's something you can kind of you can probably, yeah, not off the top of my head, but I think you can optimize in various places. So for example, you can take a minimal generating set, and that would be yeah, I think if you take a minimal generating set, that would be, I want to say it's the dimension of G, but there may be some subtleties. And then yeah, I think that's right. And then, but then I don't know how you would control for this. So that would give you some bound on M. I'm not sure how you would control this N, but I guess you would just have to go back to the proof of the lemma and see if there's room for optimization there. Yeah. But we're not, yeah, I guess we don't really need to have a small embedding, but it would be something useful to know.
Did you use the fact that GLW is finitely is a affine variety, right?
Yeah.
So this is induced from notarization. The fact that this is a netter because of from Hilbert basis theorem. So this is finitely generated algebra. Because it's inside.
This algebra?
No, it's inside the K bracket W is inside K bracket G, right? So.
What do you mean by K brackets W?
What you said before. Oh no, sorry. GL. You used the fact that GLW is a affine variety.
Yeah.
Why this is true? Why is this true?
Oh, because it's isomorphic to GLN. First,
Okay.
yeah.
Okay.
Yeah. Oh, I think we're a bit, it's already a bit past the break time. So maybe let's take a break and 5-minute break, and then we'll continue. I'll ask for questions as soon as we come back. So yeah, let's take a break now. Any questions on this proof? I know there were already a few questions. Any more questions? Okay, then let's move right along. So there's one extension of this embedding theorem that I want to point out, and that's the following. So if we have a linear algebraic group G, and we have a closed subgroup H of G, then there's a finite dimensional vector space W, and the representation of G on W. So this sort of group homomorphism, where the kernel of rho is this H. So we can, anytime we have a closed subgroup, we can find a representation where it's exactly the group elements that act trivially on all the elements in W. Okay, so I won't prove it. It's in the Samueli notes that I mentioned, that I posted a link to on the website. So yeah. Okay, so yeah, so I want to mention a few more things about this, yeah, sort of related to the things we were talking about. We were kind of thinking about this rho, which is really coming from the left multiplication action, or I guess right multiplication action of G on itself. But some of these facts are true for more general actions. So let's suppose we have an affine G-space. So X is an affine variety. We have an action map that's a morphism of varieties. And there's an associated, so we have the associated algebra homomorphism from K brackets X to K brackets G tensor K brackets X. So this is, it looks a little bit like the coproduct, except we have X instead of G. So this is actually a co-action map for this hop algebra. Maybe I won't go into that right now, but it's yeah, there's some extra structure going on here that I won't really talk about right now, maybe later on. But anyway, we have this map, and now there's a action of G on the affine algebra of X, and it's an infinite dimensional representation in general if X has positive dimension, and it's given by this formula here. So yeah, so if we have G, then it maps to the function that the linear map that takes a function f on X and takes it to this function where we first act by G inverse and then apply f. So again, it may be a bit confusing to you why is it G inverse and not G, but if you want to make sure that this is a group homomorphism, then you need to put a G inverse here. Okay, so yeah, so actually we recover the rho sub G if we think about the right action of G on X, and because it's the right action, that's why we switch the factors here. Okay, so we have that, and the also one property of this action is that if we think about K brackets X cross X, so that has an evaluation map to K, so we can just take a function and evaluate it as an element. And now I just define an action on of G on K brackets X. We already, by hypothesis, X was a G variety, and so there's a diagonal G action on here. And we think about K as having trivial action of G, and this evaluation map is equivariant. So if we take a rho of G, apply it to F, and then evaluate that at the translate of X by G, then we get a bunch of cancellation, and we just get f of x. So, and that's the trivial G action there. All right, and we have a generalization of the lemma from before. So if we have V finite dimensional subspace of K brackets X, so not K brackets G, just K brackets X, then it's contained, then it's stable under this row of G if and only if, when we do the action, this this pullback of the action map, so this algebra homomorphism, we get that it's a subspace of K brackets G tensor V. And the reason for the switch is because before we were thinking about this right action, which is kind of like a switch. So, but this is more general. And V actually has the structure of a rational representation of G. So it's a finite dimensional subspace. And in fact, this is I'll assign this as an exercise, but you can think about, you can convince yourself that K brackets X is a union of finite dimensional representations of G. So that's actually kind of nice because we can prove a lot of things about this. This is an infinite dimensional representation of G, but if we want to prove something, we end up reducing it to something about finite dimensional representations of G, and that gives us a lot of leverage. Okay, so I just wanted to point that out to set things up for this exercise. Okay, any questions on that? Great. So now I want to talk about this result. So we talked about why this map raising everything to the nth power is a homomorphism on the multiplicative group. And now I want to claim that any homomorphism of algebraic groups in the multiplicative group to itself is given by just one of these maps, x maps to xn for some integer n. So if we took n equals 0, then this would just map everything to the identity element. So it's like it's the trivial homomorphism. In particular, it's not an automorphism, but for any other n, we get an automorphism. Yeah. So so how does this work? So first we need to do a bit of algebra. So first we need this sort of lemma from commutative algebra. Maybe you've actually seen this in your algebra course. And this says that the units of this algebra, so remember that the affine algebra of the multiplicative group is just Laurent polynomials in one variable. So K brackets T plus or minus 1, T or T inverse. And the units of this algebra are just given by the following things. So we have T to the n for some n in Z multiplied by a non-zero scalar. So that's a unit. And so it's easy to see that it's a unit. And the claim is that these are all the units in this algebra. So remember, unit in an algebra is an element that's invertible. There exists another element such that the product is 1. So actually that's how the proof starts. So let F be any unit, and let's take some other, so we know that there exists some other elements such that the product is 1. So since F is a Laurent polynomial, we can write it out in this way. So n1 and n2 are just some integers, and we can take the lowest order term. So we just call n1 the smallest power of t that appears in this Laurent polynomial with non-zero coefficient. So f sub n1 is non-zero, and there is some highest order term. And we call n2 the highest power of t that appears in f with non-zero coefficient, and n2 is bigger than or equal to n1. So in general, it's bigger than or equal to n1, but we'll actually show that in this case, they're equal. n1 is equal to n2, but that'll come later. So similarly, G is just some Laurent polynomial, so we can write it out in this way, and we have that m2 is the highest power of t, m1 is the highest power of t, and these coefficients are non-zero. And because their product is 1, we know that, yeah, so 1 is equal to their product, but their product in this formulation here with the written out with the powers of t, we know that the lowest term must be this. It's just the product of the lowest order terms of f and g, and the highest term must be this. The other terms may be a little bit more complicated because there'll be coefficients from different powers of t and f and in g that come together, and it'll be some linear combination, but the highest order and the lowest order terms are easy. And so, but here we don't have any t, we just have t to the 0. So that means that, in fact, the lowest order term must be equal to the highest order term. And the coefficient must be equal to 1. So we conclude that, yeah, that the smallest power of t that appears must be equal to the highest power of t that appears. And moreover, and the sum must be 0, and we can conclude that n1 is equal to n2 and m1 is equal to m2. This product must be equal to 1. And so, well, yeah, I guess we don't even need that. We just can observe that since n1 is equal to n2, f has this form for some non-zero coefficient and some n in z. So that proves the lemma. And now what about this proposition? Well, if we start with any morphism of algebraic groups, then we know that there's a associated, in particular, it's a morphism of algebraic varieties. So there's an algebra homomorphism in the background. So it's a homomorphism from the Laurent polynomials to itself. And this homomorphism must send t here to something that's a unit, right? Because t is invertible here, so its image must be invertible. Yeah, that's the basic fact in algebra. So the image of t must be a unit in Laurent polynomials. Yeah, I guess I included an explanation of why that is here. And we just classified all the units in Laurent polynomials in the previous lemma. And we know that phi star of t must be lambda t to the n for some n and for some non-zero lambda. So the last thing to show is that this lambda is actually 1. And why is that? Well, we use the co-unit axiom. So the co-unit axiom, so we know, so since, yeah, so since we have a homomorphism of groups, it sends 1 to 1. So on the level of algebras, we have this commutative diagram. So that's, yeah, this is just a translation of the fact that any group homomorphism takes 1 to 1. And if we start with t here, then it goes to lambda t. And if we start with t here, then if we apply eta, as we said before, eta takes t to 1. But if we do phi star and then apply eta, then we get to lambda. So eta then phi star of t is eta of equals eta of t. That's what the diagram asserts. But that implies that eta of lambda of t to the n, so that's the image of t, is equal to 1, because that's what eta of t is. That implies that lambda is equal to 1. So that means that this algebra homomorphism is just given by raising t to the nth power and extending linearly. So as I said before, it doesn't mean that we take any element in the algebra and raise it to the nth power. It just means that anything in the algebra is built out of t. And if we know where t goes, then we know where everything else goes by taking powers and products and sums and so forth. Yeah, and last time we mentioned briefly that this algebra homomorphism corresponds to this nth power map, and this nth power map actually takes everything to the nth power on the level of the group. So it may be confusing. It's good to keep those two notions straight, and we already know that this is a group homomorphism. So so that proves the claim that every homomorphism from the multiplicative group to itself is given by just raising alt elements to some power. So we may actually see a different proof of this later in the course, but I wanted to point this out to show some of these Hopf algebra techniques in action, to see how we translated this geometric problem into something about Hopf algebras, and then we used various tricks and algebraic manipulations to convince ourselves of the result. Okay, any questions on that proposition or the lemma or the proofs? All right, so I think then we can move on to the next section. So yeah, we still have time, which is about the Jordan decomposition. So let me share that PDF. It should already be on the website, so you can check there. So yeah, while I'm pulling it up, you guys can go to the website and get that ready. So I've actually only prepared the first part of this Jordan decomposition lecture. I'll probably replace the PDF by the full version before the next lecture. But in any case, we have enough to start with. Okay. Great. All right. So the next topic we're going to talk about is the Jordan decomposition. So yeah, we'll see that there is sort of two classes of algebraic groups, of linear algebraic groups, that are somewhat easier to understand. These are the semi-simple or diagonalizable groups, so like tori. So those are one kind of class of groups, and the other class is unipotent groups. So basically, tori are in some sense built out of multiplicative groups, G sub n. And these unipotent groups are kind of built out of the additive groups, G sub A. And these two classes of groups will be somewhat easier to understand. We can prove lots of things about them. And in order to understand a general linear group, not the general linear group, but just an arbitrary linear group, we'll have to kind of look at the semi-simple components, semi-simple parts, and unipotent parts, and in some sense glue those two together. So the idea of the Jordan decomposition is to take so maybe I'll just state what the end result will be. We'll take any element in any linear algebraic group, and we can decompose it as a product of a semi-simple element and a unipotent element, which I'll define. And these two things commute, and this decomposition is unique. So that's kind of on the level of elements, but this will have consequences on the group level. So that's kind of the philosophy and the motivation for this section. So let's get started with the details. So here I'm emphasizing once again, I don't really need to write this, but I'm emphasizing that K is an algebraically closed field, because we'll be using that quite a bit in what follows. And now let's take a vector space, finite dimensional vector space over K. So n will be the dimension. And some terminology. So first of all, an endomorphism of V is semi-simple or diagonalizable. I'll use the two terms interchangeably if there's a basis of V consisting of eigenvectors of G. So in other words, if we write G as a matrix in this basis, then G is just diagonal. So okay, so in particular, the eigenvectors, the generalized eigenspaces of G are all one-dimensional. They're actual eigenspaces. There's no other things going on. And okay, so that's one thing. We'll discuss this in much more detail soon. So the other definition is that of a nilpotent endomorphism. So an endomorphism of V is nilpotent if some power of it is 0. So this is equivalent to saying that all the eigenvalues of G are equal to 0. And it's unipotent if the difference G minus the identity. So if we just take out the identity component, then we get something nilpotent. And this is equivalent to claiming that all the eigenvalues of G are equal to 1. So these are probably notions you've encountered in an algebra course, and then maybe in an advanced linear algebra course. So just to be a bit more concrete, what are examples of semi-simple unipotent and nilpotent endomorphisms? So let's pick a basis for V. In other words, let's pick an isomorphism to k to the n. So then endomorphisms are just n by n matrices, and any diagonal matrix is semi-simple. That's clear. Any matrix that's upper triangular with ones along the diagonal is unipotent. That's also clear, but I guess maybe the order of these should be reversed. So any matrix that has zeros along the diagonal, zeros below the diagonal, and whatever you want on the upper part of the matrix above the diagonal is nilpotent. And that's because whenever you multiply, you'll always kind of move towards that upper right hand corner, and eventually you'll get to 0. And the reason why matrices of this form are unipotent is because when you subtract identity, you're just killing all these ones, and then you get something unipotent. Then you get something nilpotent, so the original thing was unipotent. Okay, so those are just, so anytime somebody says semi-simple, you should think, okay, it's something like a diagonal matrix. Anytime somebody says it's nilpotent, you should think, okay, it's something like a strictly upper triangular matrix, zeros along the diagonal. And any time somebody says something is unipotent, then it's roughly of this form. And we'll actually prove some results that say that in various situations, we can just assume that our element is of this form if it's unipotent, and so on. So we'll get to that. But for now, you can keep these examples in mind. Okay, so I want to recall some things from linear algebra. So a Jordan block is a square matrix of this form. So there's some lambda in the field. In general, lambda could be 0. Well, yeah, lambda could be 0, but lambda is just something in the field. And that's along the diagonal. Along the super diagonal, we just have ones, and we have zeros everywhere else. So this is a square matrix. So this matrix has a single eigenvalue, lambda, and it has a repeated eigenvalue, and it has multiplicity m. And it has a single generalized eigenspace, and it has dimension m. It has only really one eigenspace, proper eigenspace, and that's the span of this first vector. But still, it has a generalized eigenspace of dimension m. And notice that if we subtract lambda times the identity, so ID just means the m by n identity matrix, and we subtract that off from J, and that's a nilpotent matrix. In particular, if we take the mth power, we get 0. Okay, and so I want to make these observations that will be useful for later on. So if we have this Jordan block J, then first of all, we can just write it as a sum of a diagonal matrix and a nilpotent matrix, so a semi-simple element and a nilpotent element, semi-simple endomorphism, nilpotent endomorphism. So that will be the observation star that I'll refer to later on. And we can also write it as a product of two matrices. So we still have the semi-simple matrix here, semi-simple endomorphism, just diagonal matrix with this is just lambda times identity. And a unipotent matrix. So it's just this. So now we have ones along the diagonal and lambda inverses along the super diagonal. So this is unipotent. And now we have a product, not a sum. And I guess I'm assuming that lambda is invertible here. So yeah, maybe I should have made a note here, but lambda, this only works if lambda is invertible. So I'll call this star star. Okay, so Is that okay with everybody? Is this, I guess this is something you guys have seen before. Okay, so those are Jordan blocks. What about the Jordan decomposition? Well, the Jordan decomposition theorem says that if we have any endomorphism, then there's a basis of V for which if we write down this endomorphism in that basis, then it has this what's known as Jordan normal form. So we take, so it's block diagonal. It's a block diagonal matrix. There's zeros over here, but on the diagonal we have these blocks. They're square blocks, and each block is a Jordan block. So each block is a matrix of the form that I showed above. So some scalars along the diagonal, the same scalar along the diagonal, and ones along the superdiagonal. These values that appear along the diagonal, so if we take all the lambdas that appear across all the Jordan blocks, those are just the eigenvalues of G, and they appear with their corresponding multiplicities. And this Jordan decomposition is unique up to reordering the basis based on a reordering of the blocks. So we can take each basis and kind of put those in different order, and we get a new Jordan normal form with different order of the blocks, but the blocks themselves will be the same. And I think, yeah, so one thing to keep in mind, just in case it's confusing, is that each Jordan block has a single eigenvalue. There's only one eigenvalue that appears in a Jordan block, but a given eigenvalue can appear in multiple Jordan blocks. So we could have, if we had an eigenvalue 5, there could be several Jordan blocks of different sizes with that eigenvalue. Okay, so yeah, so let's kind of abstract this a little bit. So we can say that, so this lemma will just be a consequences of what we said before. So if we have any endomorphism little g, then there are elements S sub g and S sub, that should be an n. Maybe it looks like a u, but it's an n. And there's other endomorphisms G sub S and G sub n. With the following properties. So G sub S is semi-simple. G sub n is nilpotent. Their sum is equal to G, and they commute. So G sub S times G sub n is equal to G sub n times G sub S. So yeah, so why is this true? Well, we just, okay, so proof. So we know that there's a basis of V yielding the Jordan normal form of G. So we take that basis, and in that basis, we have this diagonal. We have each Jordan block, and each Jordan block we can write as a sum, as I observed above. And if we take that sum and put those together again into block diagonal matrices, we see that one matrix will be semi-simple. It will just have all the eigenvalues along the diagonal, and the other matrix will be nilpotent. You can also check that they commute. So this is just a computation on the level of one Jordan block. And yeah, that's all that's going on. So, so great. So we have that. So I just want to point out that if we look at the collection of eigenvalues of G counted with multiplicity, that's the same as the eigenvalues of G sub S counted with multiplicity. Okay, so now we get to a little bit deeper result, probably something that doesn't appear in a linear algebra course. So if we have, let's take an endomorphism G, and let's take this G and S, G sub S and G sub N that appeared in the lemma. So basically coming from the Jordan decomposition. Then, so the first thing we'll claim is that these matrices G sub S and G sub N are kind of coming from, can be written as polynomials in terms of the original G. So more precisely, there are polynomials P and Q. So we think of them as abstract polynomials in a variable T. And we have this condition that P of 0 is equal to 0 and Q of 0 is equal to 0. And P of G will be equal to G sub S and Q of G is equal to G sub N. So this seems maybe a bit, I don't know, strange to have this ask for these sorts of polynomials, but this will be very useful because what will happen is that, for example, if we know that some element commutes with G, then because G sub S is just a polynomial in G, then that element will also commute with G sub S. So that's how we'll be using this result later on. So so that's the first part of the proposition. So the second part says that these two elements are uniquely determined, satisfying the conditions of the lemma. So maybe we could have had some other Jordan decomposition, but in fact, it'll turn out to be the same as the one we had before. And then finally, if we have a subspace of V, W, that's G stable, in other words, G takes G, so G is an endomorphism of V, and if G takes W to itself, then it's, first of all, it's stable for the semi-symbol part of G and for the nilpotent part of G. And there's this nice interaction. So if we restrict G to W, then that's an endomorphism of W. So that has a semi-simple part and a nilpotent part. And those coincide with the restrictions of the semi-simple parts and nilpotent parts of G. So that's what's going on there. Okay, any questions about the statement of the proposition before we jump into the proof? All right, so what's going on? How do we prove this? Well, first of all, we need some notation. So first of all, you'll recall the characteristic polynomial of G. So this is the determinant of T times identity minus G. But we can also write it in terms of the eigenvalues. So the eigenvalues are precisely the roots of the characteristic polynomial counted with multiplicity. And if we take, so let's let lambda 1 through lambda r be the distinct eigenvalues of G, and n sub I will be the multiplicity of lambda sub I. So then the characteristic polynomial factors as this product, T sub lambda I to the n sub I. This is a polynomial in T, in one variable. So that's a characteristic polynomial. So more on that in a bit. So I just also want to introduce some notation here. So for each of these lambda I, so for each of these eigenvalues, the distinct eigenvalues, we have a generalized eigenspace of lambda I. So what is this? Well, this is the vanishing subspace of this endomorphism. So G minus lambda sub I. So really by this, I mean lambda sub I times the identity endomorphism of V, but I'm just going to suppress that notation, and I think this is clear. G minus lambda I to the Ni. So all the vectors that vanish under this endomorphism. So if Ni is equal to, if we didn't put Ni, if we just had G minus lambda I, that would be the eigenspace, but because we allow ourselves this Ni, we get the generalized eigenspace of lambda I, and we have this direct sum decomposition. So this is just linear algebra. This whole proof will just be a whole bunch of linear algebra. Okay, and we also need to recall this fact. So I guess it's called the Chinese remainder theorem. I don't think I learned about it under this name, but that's what it's referred to in Springer and also in the Samueli notes. So this basically says that, so we have this polynomial algebra in one variable, and we want to mod out by the characteristic polynomial. I'll say in a little bit why this is what we want to do, but let's for now just consider what happens when we mod out by the characteristic polynomial. Well, we factored the characteristic polynomial in terms of its roots. And each t minus lambda I defines a maximal ideal. And yeah, this theorem says that basically this quotient is isomorphic to this direct sum of rings. So each one of these is a different ring, and we have this direct sum decomposition. Right, and so now what we want to do, and this will seem mysterious here, but I hope that as we go on in the proof, it'll become clear why this is the right thing to do. We want to take an element here, namely we want to take the element that has just lambda I in each factor. So we just take a constant in each factor. That constant is lambda I. By this isomorphism, we know that there's some p of t, some polynomial, such that when we mod out by t sub lambda I, to the ni, we just get lambda I. So we use this isomorphism in this way. And yeah, does that make sense? Why we can make this choice of polynomial? Okay, I guess so. Then I'll move on.
Lambda
So,
is not a scalar, right?
Sorry?
Lambda is a polynomial, right? Lambda.
Yeah, lambda you think of as a polynomial, just a constant polynomial. So
Okay.
no t's. Yeah, lambda I times t to the 0th power. Yeah. Okay. So now a little claim. So this p of t that we've chosen, we can change it so that it's that p of 0 is equal to 0. So why can we do this? Well, yeah, this is not an important part of the argument, but if the characteristic polynomial evaluated to 0 at 0, then that means that 0 is a root of the characteristic polynomial, which means 0 is an eigenvalue of g. And so then one of these lambdas is equal to 0. But then how did we choose t? Well, we chose t to be equal to each of the lambdas, mod t minus lambda I to the ni. But if for that specific lambda that's equal to 0, we get that p of t is congruent to 0, mod t to some power. And so then t of 0 has to be equal to 0. Okay, so that's case where phi of 0 is equal to 0. Phi of 0 is not equal to 0, then we can replace p by this. So p minus p of 0 divided by phi of 0. So these are just scalars times phi. And p prime of 0 is 0 by construction. And p is congruent to p prime mod phi because we got p prime by just adding or subtracting some multiple of phi from p, so they're equal mod phi. And we have this, we use the Chinese remainder theorem again, because the quotient, we only choose p up to phi, because we mod it out by phi here to get this isomorphism. Okay, so yeah, that's just some basic linear algebra. So now the next thing we want to show is that this p that we chose, if we plug in g into this p, we get the semi-simple part g sub s. And now maybe it's a bit confusing. What do we mean by this p of g? What do we mean by plugging in g? Well, really what's going on here is that we have an algebra homomorphism from the polynomial algebra to the endomorphism algebra of V, where we take t and we map it to g. So g is an element. This is like the free commutative algebra on one variable. So we can just say where t goes. It doesn't need to satisfy anything. I guess it just needs to be non-zero maybe. And then we it could even be 0. And then we extend this to an algebra homomorphism, and that's what we have. And by P of G, really what I mean is this, the image of P of T, this polynomial that we chose under this algebra homomorphism. And I want to point out that so we have a basic fact that G satisfies its own characteristic polynomial. So that means that this row factors through the quotient of polynomials by the ideal generated by the characteristic polynomial. Okay, so I'm running low on time, but maybe I'll just prove this claim and then we'll call it a day. But this is kind of important to kind of conceptualize what's going on. Does this make sense to people? Okay, so I hope this proof isn't too long, but yeah, so how do we prove that P of G is equal to GS? Well, first of all, let's note that each of these generalized eigenspaces is stable under G, so G preserves them. Well, to do that, we just check what the definition of these are, and we see that we get the appropriate thing. And because each of these is stable under G, we have a different algebra homomorphism that just takes from polynomials in one variable to endomorphisms now of just VI, and this takes T to the restriction of G to VI, so that maps VI to itself, so it makes sense. And now there should be an I here. So now if we take rho sub I and we think about this polynomial, T minus lambda I to the Ni, then, okay, by definition, that's G restricted to Vi minus lambda I. Now, lambda I, you think of it as lambda I times the identity on Vi to the Ni. So that's just what it means to extend this algebra homomorphism to from this definition to the whole polynomial algebra. But now this whole thing is congruent to zero on it's just, I mean, not congruent to zero, it's constantly zero on Vi. Why is that? Well, it's just the definition of Vi. Vi was all the things that vanish when we applied this operator. So by equal to zero, by congruent to zero, it just means that it's constantly equal to zero. So that means it factors through this homomorphism factors through the quotient by this ideal, and we have the following commutative diagram. So since this rho I maps this polynomial to zero here, we get this factorization, and yeah, this is just the quotient map, and then we get this computation that I'll let you look at. But basically, we compute P of G restricted to Vi. We have a string of equalities here. So first of all, the first equality comes from the community of the diagram. The second equality comes from our choice of P of T. And then we get that this is just lambda I times identity on Vi, but that's exactly what GS is. So thinking back to the Jordan decomposition on each Vi, this GS is just a diagonal matrix, lambda I times identity. And since these VIs, their direct sum is V, since they span all of V, and we've shown that P of G is and GS coincide on each VI, we get that they're the same thing. Okay, so I think I'm out of time. I can stay for a couple of minutes if anybody has any questions.
Just what is the purpose for all this computation?
Yeah, so what we want to show is that that P of G is equal to GS.
Oh, I mean, what is the purpose of the theorem? Of the Jordan decomposition? Okay.
So
the teaser for next week.
So it's the purpose, well, as we'll see next time, the purpose is to kind of generalize it to this. So now we're only thinking about endomorphisms of V, but what we'll see next time is that we can extend this to GOV. So not endomorphisms, but invertible endomorphisms where we don't have a nilpotent element, but a unipotent element. So, and then from GOV, we can generalize it to any any linear algebraic group. So any linear algebraic group will have a decomposition. Well, any element in the linear algebraic group will have a decomposition into a semi-simple part and a unipotent part. And the starting point of all this is just this linear algebra Jordan decomposition where we take an endomorphism, so not something invertible necessarily, but an endomorphism, and split it up into a semi-simple part and a nilpotent part. And we build on this idea to get something that's true for all linear algebraic groups. So yeah, so right now maybe the motivation is not super clear, but we'll get to it. Does that? Okay.
Yes.
Great. Any other questions? All right, well, if anything else comes up, feel free to email me, and I guess potentially no TA session. If there is some, I guess Shivi will let you know. Otherwise, I guess I'll see you next week. Thanks, everybody.
Thank you.
Thank you.
Bye.
Thanks.